For this problem, we want to solve a third-order homogeneous equation. And just like before, we take our e to the RT, which is our solution, and we take the derivatives that we need. So y prime of t is r e to the RT. The second derivative is r squared e to the RT. And now our third derivative is going to be an r cubed e to the RT. If we substitute all of those in, we will see something similar to the second order equations. We'll have an r cubed e to the RT minus a 2r squared e to the RT minus an r e to the RT plus 2 e to the RT equals 0. Once again, we can factor out the e to the RT, leaves you with r cubed minus 2r squared minus r plus 2 is equal to 0. And once again, we can cancel out the exponential by dividing both sides by it, and we get an r cubed minus a 2r squared minus r plus 2 is equal to 0. This is still called an auxiliary equation or a characteristic equation, but now we cannot use the quadratic formula because it's cubic. So we have a couple of choices. One, we could just kind of guess some solutions and divide to reduce the order down, or you can go to a graphing calculator and find at least one real root that's guaranteed to exist and then divide it out. So if you graph this on a calculator, you will see that it's going to cross as a cubic polynomial something like this right here. And you'll notice that these locations can be found using the trace feature, and one of them is a 1. And you can also notice that if you just substitute 1 into this equation, 1 minus 2 minus 1 plus 2 does make 0. So now that we have one of our roots, we can use synthetic division to divide our polynomial down to a smaller ordered polynomial. Once again, to do this, we just copy the coefficients off of the polynomial. So we're going to have a 1 from the r cubed, a negative 2 from the r squared, a negative 1 from the r, and a 2 from the constant. And if we had a term missing, of course, we use 0 to fill those spaces in. We now bring down the 1 and multiply. 1 times 1 makes 1. Add them together. We get negative 2 plus 1 makes a negative 1. Multiply them together. We're going to get negative 1 again. Adding those numbers up, we get negative 2. And then negative 2 times 1 makes, well, negative 2. Adding gives us a 0. And that's our remainder. And we need to have that 0 there for remainder. Otherwise, we don't have a root of the equation. So next step is now to rewrite. We know we've got an r minus 1 because 1 was one of our roots. And then we now decrease our order as r squared minus r minus 2 is equal to 0. This quadratic can now be factored down further as an r minus 2 and an r plus 1. And that tells us that the other two roots are positive 2 and negative 1, and those are over here on our graph, our negative 1 and our positive 2. So the three different values of r we got are r1 equals 1, r2 equals 2, and r3 equals a negative 1. So our solution, because it's a third order equation, is going to have a third arbitrary constant. We're going to have c1 e to the 1t, our c2 e to the 2t, and now a third arbitrary constant, c3 e to the negative 1 times t. And this is the solution of that third order linear equation. And you will notice that we can check linear independence by going through and finding a 3x3 Wronskian. And you could take the first, second, and third derivatives, substitute them into the original equation, and you will get 0, verifying the equation is true.